including on the survey. I think we had a great lecture to open the day with a lot of questions by the student. So I think, so far so good.
Yeah, must be
Thank you.
very early there.
Yeah, I mean, yes, I've been up since 3 a.m.
Okay, great. Thank you. Now, okay, for the students who's already in the classroom, please join us, open your video camera so that your lecturers can see you and can interact with you. Okay, so we have at the moment at least 53 in the classroom now. All right. Okay. So, yeah, so I will start introducing our next lectures for today, so that we're not, so that we have enough time later for the lecture and for the quiz for the Module 5. So we're continuing the Module 5. This is Module 5B. Now, Molecular Dynamics, Understanding Structure, Function, Dynamics Relationship. So here we have our distinguished lecturers. We have here Dr. Yuji Sugita. Dr. Sugita, you can wave hi to the students.
Hi, my name is Yuji Sugita from Japan again. So nice to meet you.
Yes, nice to meet you. So I would like to briefly introduce Dr. Sugita here. As he said, he's the team leader of the Laboratory for Biomolecular Function Simulation, RIKEN Center for Biomolecular Dynamics Research, Japan. Dr. Sugita received his PhD from Kyoto University and a postdoctoral fellow at RIKEN. He has received several awards, including the Young Scientist Award of the Physical Society of Japan, the Morino Science Award from the Morino Foundation for Molecular Science, and the Young Scientist Award of the Molecular Simulation Society of Japan. So welcome, Dr. Kobayashi, Dr. Sugita. And another one, I'll just briefly introduce Dr. Kobayashi.
Recording in progress.
Hello.
Hello,
My name is
Dr.
Chigusa Kobayashi. Hello. My name is Chigusa Kobayashi from RIKEN in Japan.
Yes.
Okay, nice to meet you.
Nice to meet you. So Dr. Kobayashi here is a technical scientist at the HPC Usability Development Unit, RIKEN Center for Computational Science, Japan. Dr. Kobayashi is also a technical scientist at the Computational Biophysics Research Team. She has been in her current position since 2020. Her research interests include computer simulations of biological systems like membrane proteins and soluble proteins. She has investigated structural changes of protein and developed models and its method. So Dr. Sugita and Dr. Kobayashi, please, the sessions are yours. Thank you.
Okay, so can I share my screen?
Yes, I think so. Yeah.
Okay. So can you see the slide? Okay, I can start. Okay, so yes, it is my great pleasure to talk about molecular dynamics simulation of biomolecules. And this simulation is aimed to understand structure and function and dynamics relationships of biomolecules, such as proteins and nucleic acid and so on. So today, I'd like to briefly discuss about the why molecular dynamics is necessary and what we can understand from this simulation. Okay. So this is the content of about two hours lecture and hands-on tutorials. So I, Yuji Sugita, will give a lecture about the basics of molecular dynamics simulations for biological systems. So I plan to spend about 20 minutes 20 minutes. But and after the lecture, I welcome questions and also discussion from the audience about 10 minutes. And if there are more questions, so I'd like to answer your questions later on. And after my lecture, Dr. Kobayashi will explain the hands-on tutorials of analysis of MD simulations. So she will first spend some time for explaining the procedures by using her PowerPoint file. And then she explained how to do the analysis using Google Collaboratory or Jupyter Notebook. So you can enjoy these hands-on tutorials, which will be explained by Dr. Chigusa Kobayashi. So, and just after hands-on tutorials, we plan to do a quiz for checking your understanding of our lectures. That is a plan. Okay. All right, let's start the lecture. So, in fact, I don't quite understand your background of in your university. So, because of this, I'd like to start very beginning of the biological systems. So, this slide explained how much each biomolecule exists in the cells. So the left graph actually shows that the most abundant molecules in our body is actually water, right? So at least 60% of the volume or molecules exist as water. So otherwise, we can be very thirsty, and probably if we don't have sufficient water, we may die. So water is very essential for any biological molecules. And next abundant molecules are actually proteins, which I will talk mainly today. And the third rich molecule is fat, and the other one is carbohydrate or others. So you can see the chemical representation of phospholipid or carbohydrate in this way. Okay. So today I will plan to talk mainly about proteins. So briefly, I'd like to explain what is a protein. So actually in high school textbook of biology explain what is a protein. So protein is actually made up of a long chain of amino acid. So in this cartoon, so you can see many bees are connected in a single chain like this. Okay. And if you close up this this part, actually the chemical structure can be seen in this way. Okay. So each color of the bees actually represents an amino acid. So it means that the red and yellow and orange and blue circles represent different amino acid. But they are actually connected, bonded by forming peptide bonds. So this way, right? You can see the same bonds, chemical structure here and there. So in this way, amino acid form proteins. Then the next, I'd like to explain about the what is amino acid? So amino acid are the very important components of proteins. And we know that there are 20 amino acid types. So in like these figures. So indeed, each amino acid has different chemical and physical features, characters. So some of them are actually non-polar or charged. No net charge, I mean. And however, sometimes some of the residues amino acid has plus charge, like lysine, arginine, and histidine. So they have plus one as amino acid. And some others, like aspartate or glutamate, have minus charge. So previous one was plus, but this one has minus charge. And these four types are polar amino acid, but they don't have net charge, so zero charge. And this orange one, non-polar and uncharged residues, amino acid, but they're quite hydrophobic. It's like oil, and kind of features. And glycine and cysteine and proline has quite unique features. Okay. So in particular, I'd like to emphasize these bases, plus and acidic minus amino acids. So they have quite unique features and add functions into the proteins. Okay. So as I mentioned in the previous figures, so amino acid, a series of amino acid form a protein, right? But if we look at the structure of proteins, we can easily found that there are several quite repeated structures. That is, we call secondary structures. And we know two very important types of secondary structures. One is beta sheet, like this ribbon, okay? And another one is alpha helix. Helix is, this shape, these helical structures. And these two are quite common features of structure features in amino acid proteins. So the protein is uniquely determined from amino acid, and then it forms these repeat order structures, so alpha helix or beta sheet, and finally it forms the three-dimensional structures. Okay, so we can show you some example of the sequence and structures. Sequence means that a series of amino acid. So D is aspartate and Y is tyrosine and K is lysine. So this one letter character represents one amino acid. So you can see the sequence of the amino acid. And this sequence actually is GPCR proteins. So this is sequence and this is structures. And second one is so it consists of 1,295 amino acid residues. And so by using these many amino acids, so it forms the one protein structures. That is toxin. And this is actually food poisoning causes. Okay, so now you can understand the relationship between amino acid sequence and three-dimensional structure of proteins. Okay. So what next is actually molecular dynamic simulation, which we are working in computer simulations. So now you understand the protein has structures like previous slide. So what do we want to do in the calculation is to understand how to, move the structure in the atomic resolution. So that is molecular dynamics simulation. So as you can see, by using computer simulation, we can predict the dynamics of these molecules in computers. So here, a yellow molecule is a protein, and blue small one is actually water. Because protein usually exists in solution, so we have to simulate both protein and water. So that is a requirement. So how to make these movies? So we perform MD simulation. That is actually quite simple, based on very simple theory. That is Newton's equation of motion. So F equal ma, right? M is mass, and A is acceleration, and F is the force. So I think you can learn this equation in high school, but in computers we don't solve the equations in this form, but we usually use this type of the equation. And in fact, this equation and F equal ma is equivalent. However, in computer simulation, we use the time step delta t. So this is quite very short time, actually 10 to the minus 15 seconds, typically. And in a simulation, we start from one structure and one velocity, and integrate this equation to show the time progress a little bit, just 10 to the 15 seconds. And then we can get the next structures. And next structure can be used, again, the same equation to get the next structures. So in this way, we can solve these two equations iteratively and so many times. And then eventually we can get the series of coordinates and velocities. So that is the very, very basic of MD simulation. And if you get all the data together, so you can make this kind of movies. And also you can compute any properties of the dynamic systems. So that is the basic theory of molecular dynamic simulation. Okay. So so as you already know, the simulation itself is quite simple, so based on very simple theory. However, in fact, if we apply this calculation to the real protein system, so it requires a lot of computations, and we have to spend so much computer powers. And the previous example was actually very small protein, but in our cell, there's so many proteins, and much more complicated molecules. So we have to spend huge computer time and compute our computers, or GPU, or even supercomputers. So to utilize supercomputers for molecular dynamics simulations, so we developed our own MD code, which is called Genesis. So in fact, Genesis is a free software, and everyone can download our software from this website. if you have interest. And this is really free software under LGPL3 version 3 license. So yeah, you can freely use for your research and yeah, for the purpose. And in fact, there are many other MD simulation softwares. So GLOMAX or AMBER or CHERM or NAMD or yeah, many other softwares. So what is the key feature of software is actually, we think that two key features. So one is using supercomputer or GPU clusters, we can perform very large scale MD simulations with high performance. So that is one of the key features. And another one is, this is a little bit complicated, but we can sample so many conformations of proteins or other biomolecules very efficiently using some methods based on statistical mechanical theory. So based on these two features, so we can utilize the this kind of supercomputer powers very effectively to our computer simulations. I can show you one example. So that is strong scaling of our program Genesis, the latest version 2.0 beta on Fugaku. So probably you may hear the Fugaku supercomputer. This is actually my background. So yeah, you can see these computers. So in Kobe, there's many CPUs available on Fugaku, and this machine shows the most strongest powers supercomputer in the world. So I think the last year we used this computer and performed a benchmark and to show the very good strong scaling of our program. So for this, as a benchmark system, we use very big system which contains the 100 million atoms or even 800 million atoms, or the largest one, the red one is actually billion, more than 1 billion atom system. This is actually almost the world record of the MD simulation in terms of simulation size, system size. But even for the largest system, you can see the very good strong scaling. So if you use more CPUs, so you can get better performance in this way or this way. Right. So yeah, so by using the program Genesis on Fugaku, so we can get very good performance. This is also applicable to a smaller system. So this is a spike protein in oscilloscope 2. So I will explain it later. The second features, this is a bit complicated. So if you don't have the background of statistical mechanics, so you don't need to understand the detail. But just I'd like to tell you the key features of the method. So in MD simulation, so we can set temperatures of the system. So at low temperature, we can explore the the low energy state, something like here or there. However, in the low temperature simulation, so if in the potential energy, so many barriers exist, the simulation cannot overcome such barriers at low temperature. But if we perform simulation at high temperature, we can easily overcome this kind of barrier, because at high temperature, so the molecule is more mobile due to the heat. But it is difficult to explore the low energy state, but this is very important. So in one of the enhanced sampling method, replica exchange MD, which we developed very long time ago. We mixed such low temperature simulation, high temperature simulation by mixing the temperature with different replicas. So in this way, we can explore both low energy states and also can sample many other conformations. So in this sense, this is quite efficient. And so you can see that the publication year, so it was actually more than 20 years ago. And a new method was published quite recently. They are quite similar, but the new method, which we call G-REST, is applicable to very large system now. So we are now using this method for spike protein simulations. And other interesting feature of MD simulation is that the mouth scale method. So here, the top molecule, they're actually the same, but resolution of the model is different. The top model is based on atomistic model. So we treat each atom as particle. So this is quite fine, but very expensive calculation. But in the bottom model, that is we call coarse-grained model. And in this case, one particle is actually one amino acid. So chemical detail is neglected. So this is much, coarse and inexpensive model. But if we, select the parameters to mimic the atomistic model or experiment, so this coarse-grained model is still quite useful if we, want to study multiple proteins dynamics or, very complicated system. Okay, so from now on, I'd like to explain two applications. So one of the applications is actually the simulation of cytoplasm. This is not molecule, but this is, collection of the protein and other molecules. So this simulation was performed using K computers, the previous Japanese supercomputers, but the same software Genesis. And we performed Genesis on the 100 million particle systems, which represents bacterial cytoplasm. So you can see that not only one, but many, many proteins exist in a crowded environment, and they interact with each other. And also, you can see a small molecule like ATP or GTP or something, amino acid. So in the cell, so yeah, it is highly crowded and with many other proteins and biomolecules, but they interact weakly or strongly to, for their functions. That is in reality. So we can achieve more realistic simulation using supercomputer powers. That was done 5 years ago. And next example is more recent application that is related to SARS-CoV-2. So I think that not only Japan, but all the world was quite influenced by this virus. So, and everyone is suffering from this virus now. So the key feature of the virus is on the surface of the virus. So many spike is observed. So spike is actually a protein, and we call this spike protein like this. So there are many interesting features of spike proteins, in fact. And one of the important feature is the protein surface is actually contain many glycans, saccharides like this. Yeah, so if you close up this glycan, you can see these chemical structures. So this glycan is very important. So for the function of the virus, because the virus infection damage human, but in human body we have immune system. So by making the antibody, and human body try to prevent the infection. So and then the virus itself also try to infect. So this is the fight between human and virus. And for the virus, strategy is to avoid the attack of the antibody. So they prepare the glycan to protect their structure. So this is more detailed explanation about the how spike protein is infected to a human host cell. So we already know many things about this infection. So one of the feature is important information is a receptor in the human cell. That is ACE2 receptor. So this membrane protein actually binds spike protein in the very, very beginning of the infection. That is the start of the infection of the SARS-CoV-2. So, the vaccines and drugs, so many of our efforts target to this protein. So, we can, many people now finish the vaccination, but the target of the vaccine is actually the spike protein. And we try to make the antibody so to target this spike protein after the vaccination. And in a microscopic view, we know that spike protein has different conformations. So that is down conformation. This is inactive. So this structure cannot bind to the ACE2 receptor, but the other form, up structure, can interact with ACE2 receptor. So we try to prevent this conformational change from down to up. That is one of the ultimate goal of the simulation. But so still our research is very, very beginning of the story. So we just started the mystic MD simulation of spike protein in water with glycans. That was what we did last year. So using Fugaku and Genesis. Okay. So by this simulation, we try to understand the conformational change and also to understand the functional role of glycans on the surface of proteins. So today I don't have enough time to explain everything, but we prepared the nice movies for explaining what we learned from the simulation. So I can show you the movies. So before starting, so you can see that simulation setup. So one structure that is downform inactive, but with glycan on the surface of spike. And the other one is up, starting one up structures. It's not so clear, but here, this receptor binding domain, right? This is the up structure, not down. So these two are different. So we perform both simulation for 1 microsecond using Fugaku. So, Yes, so by performing MD simulation, so solving Newtonian equation of motion, so you can see the dynamics and how this protein move in the water. And then after the simulation, we analyze the simulation trajectory and to focus in this study. So what is the role of glycan? And we see that these three glycans are very important. So they are the orange is 165, and yellow is 234, and green one is 343. So you can see that in down form, inactive, and up form, active. So three glycans functions are different. So here, yeah, so you can easily see that 343 interacts in down form, but it is separated in up form. And yeah, so like this, by performing MD simulations, so you can see the very detail of the molecular interaction. That is the outcome of this simulation. You can see once again about the movies. So we actually simulate also water, but neglected. Yeah, so these N3/4 interact in this way, so in up, but it's totally different for the down form. So in this way, so this simulation is not quite long, but we can observe that interesting feature of the dynamics of spike protein on the surface of SARS-CoV-2. Okay, so let's summarize. So in a spike protein simulation, so we can simulate the dynamics of in the down form and up form. And by analyzing the simulation, we can study the functional role of glycans on the surface. So they're actually different for down form and up form. Okay, so this is the last slide of my talk. So I can switch to questions, okay? Okay, so from now on, I'd like to welcome your questions and discussion. Okay, so I can see the chat box. Okay, so there are yeah, so actually two questions, maybe. So the first question, yeah, I did the first question. So referring to John et al. 2021, is the SARS spike protein used appeared under a native form? If the target protein is bound to inhibitors, can't it be subject to MD? Oh, it's quite a professional question, I think. So, you know, the, sorry, my video is stopped, but I'm okay. So, the structure of spike protein, which we used, actually taken from the cryo-electron microscopy experiment. So experimentally, the structure is taken by such method. So nowadays, I think more than 100 or 200, I don't know how many, but so many different cryo-EM structures are available for spike protein. We use two of them as a starting structure of our simulation. And the second question is, Of course, yeah, we can include inhibitors or even antibodies in a simulation. In fact, now we are working on the spike protein and antibody complex to see how the dynamics is changed. So that is the answer to the first question. Okay, the second question, it's quite long. So, but we did molecular docking of multiple molecules against SARS-CoV-2 and Pro. Yeah, that different, but the very important proteins, and obtained promising inhibitors by comparison to the docking scores of the known in vitro inhibitors of mPro. Oh, that's great. Yeah, and we want to perform molecular dynamic simulations for our promising molecules, but we are currently limited by computational power. My question is, what is the minimum MD time necessary to preliminarily assess the stability of interaction between residues and our molecules? Oh, that's good questions, but very difficult to answer because how can I say? So the docking and MD have a bit similar but have different philosophy. So docking, so as you may know, you can perform many docking, rigid body dockings. So to rigid, but this case the protein and most likely proteins and inhibitors structures are treated as rigid. But MD, so we are treating the conformation flexibility. So it takes much longer time. So in our case, we performed 1 microsecond simulation, but that is okay for just see the fluctuation around the down form and up form. But to switch two structures, it is totally not sufficient. So in this sense, I cannot say easily the minimum MD time. So, but at least in the current standard, you have to perform several hundred nanoseconds, or if necessary, at least microseconds. But it's totally up to the biological phenomena. So it's a good question, but very difficult to answer, in fact. Okay, let's move on to the next question. So just curious, what is the functional difference when protein in down form versus up form? Yeah, again, this is also excellent question. So, we consider the down form is kind of resting structures, and up form is the active, and it can bind with the human receptors. So, the antibody development, so we have considered how to keep the down structures. If, we can make the drug or antibody which can, fix the spike protein structures as down form, then, it become much safer. But so there are many large intrinsic motion of the spike protein. It is not so easy. So that is the current situation. And also, as you may know, the mutants may change the binding with antibody or drug. So the situation is very complicated. Okay, let's move on to the next question. Since you mentioned that a few software for MD simulation besides Genesis, could you compare and contrast each one, please? I never done an MD simulation before, thank you. Okay. So I think that, first of all, there are many different point of views for comparison. So first one is price. The Genesis is free, but you can find many other free software. But for instance, Schrodinger's software are very nice, but commercial, very expensive. So you can find that free or commercial software. That is one important thing to use. And even free software, you can find many softwares like the, except for Genesis, that Glomax is quite famous. And NumD is also very good. And OpenMM is also very nice. And yeah, LAM-MPS is very useful for material simulations. So other consideration is the size of the target. So for instance, so GPU is very useful, and actually price is also not so expensive usually. So OpenMM is quite a good software for using one GPU, but it is very difficult to parallelize. Actually, not possible to use the parallel GPU. But Genesis, we can use the multiple GPUs at the same time. So that is one feature of Genesis. But you know, there are so many other points, but I cannot tell you everything. So I'm sorry. Okay, let's move on to the next two questions. So that's what is the functional difference of this? I think that I already answered. So final one is for REMD sampling method. What are the temperature range for high and low? What criteria are taken into consideration at setting the temperature range? Oh, this is very excellent and professional questions. And low temperature is very easy. So that is usually room temperature, 300 Kelvin or a little bit below. Okay, so that is choice is very easy. High temperature is a bit more complicated. So high temperature is necessary for enhancing sampling, so exploring many conformations. Of course, higher is better, but if it is too high, this is actually many parallel MD simulation, and you need more and more replicas, more and more MD simulations. So the competition costs become higher. So the criteria is usually the overlap of the distribution for each temperature simulation. And if the two simulation results totally separated, no exchange happens. So this is replica exchange MD simulation. So replica exchange is essential. So we have to make at least neighboring replicas distribution overlapped. That is quite important criteria. So there are several servers to estimate the temperature range. So you can use such servers. Oh, one more question. Okay, probably this is the final question to answer now. So of course you can ask me the question later, then I can reply to you later. Okay, so this can be the final question before Kobayashi-san talk. Okay, so I was a bit confused that in your MD you start two confirmation, down and up. Yes, that's true. Realize up confirmation able to bind to RBD. My question is, if we only use one initial structure, either down or up in MD, can this convention change to prefer binding mode if we include RBD in our system? Or we always need starting with different initial structure for different systems? Oh, that is also very good question. So first of all, this spike protein system is a very big system for us. And it is not so easy to simulate the conventional transition, so from down to up, right? But in fact, by using our replica exchange MD, so we can almost achieve such transition in the latest results. But in the previous studies published in Biophysical Journal, we just simulate each structures separately. due to the insufficient computer time. So 1 microsecond is not sufficient to simulate such conformation. Our ultimate goal is just from one structure to explore many other existing structures. That is our ultimate goal. But usually, that is not so easy using just conventional MD or even enhanced sampling method. So this is still a future challenge to find to develop such better sampling strategies, which is applicable to many other biomolecules. That is still, the open questions and future work. That is my comment. Okay, so Kobayashi-san, can I switch to you? Okay, so thank you very much. And if you have more questions, so please don't hesitate to ask me questions. I try to answer as many as your questions. So thank you very much. So, and I'd like to switch to Kobayashi-san. Kobayashi-san, please.
Thank you very much, Sugita-san. So, hello, my name is Chigusa Kobayashi from Riken RCCS in Japan. So now that I'm going to, going to move on to the hands-on tutorial. So this is the third part of our lecture. So the hands-on tutorial of analysis of the MD simulation. So as Sugita-san told, so first I would like to briefly explain about the our tutorial and the procedure of the MD simulation using this PowerPoint file first. Then we can move on the hands-on tutorial using the Google Collaborative or Jupyter Lab. Okay. Then this is today's tutorial. So because we have already prepared the tutorial, so for the how to understand how to execute the genesis and using the genesis trajectory. So this is the one of this project tutorials. So this website is here. So if you access this link, you can find the 3 levels: basic, standard, and advanced. So then you can find you can learn how to execute the MD simulation or analyze the MD simulation, including the normal MD simulation and replica exchange simulation, or so on. However, today's lecture, since MD calculation requires a lot of the computation resources, we will not perform the MD calculation itself in today's hands-on session. Instead, I already executed the MD simulation of this tutorial and put on that log file. Then, by using these log files, so then you can learn the procedure of the MD simulation today. So, part of the tutorial is in the form of a Jupyter notebook, so that I hope that you can easily learn the procedure MD calculation. So if you are interested in the MD simulation and our tutorial, our software, so then please go to our website and see in that tutorial page. Then I'm going to talk about our materials. First, I prepared the 2 types of materials. First one is you can select either of them. So first one is I recommended this one, so the Google Collaborative. So I pasted the link, and you can get the link from this PowerPoint file. So if you access these links, you can see this website. But so please wait. I first talk about this PowerPoint or later we can back to this link. So second one is not, if you can't use the Google, so then I also prepare the Jupyter Lab. So if you prepare the Jupyter Lab, so then you can download the notebook from this site. So I also I prepared the two types of notebooks for the Windows and Linux or Macintosh. So you can select it either of them. So, and if you just start up the Jupyter Lab at first, then load it this notebook. Then you can do that. But I will not explain this one so deeply today. Then I'm going to talk about today's procedure. First, I'm going to talk about the preparation of today's hands-on tutorial. So this is a not MD procedure. So from the second, this is a procedure of MD simulations. So first part, set step is a set up simulation system. Second one is a minimization. This is it minimizes the potential energy to remove the unstable steric classes. Third one is equilibration. So this step set the temperature and pressure for the simulation box. Fourth one is production. So production is I think the researchers think that this step is an MD simulation. The MD simulation for the analysts get their trajectories and the structures or energies, so on. So final step is analysis. So after we get the trajectory from the MD simulations, we need to analyze the energy or structures as Sugita-san showed in previous path. So then that is also quite important. So I'm going to talk about this procedure one by one. So first one is the preparation of the tutorial. So today, so later on, so please access this link. Then during this tutorial script, so uses the 3 Python modules, so py3d matplotlib, and then the extract data from the Genesis log file. But you don't need to care at this moment. I will explain later. So, yeah, okay. So then I would like to talk about that. So how to execute the command on the Google Collaboratory. So after you show that website, you can see that gray shade box. So if you would like to execute that command, so please click here. Then please enter the shift plus enter or return in your keyboard. Then command will be running. So, and you can see that this icon, so the round icon. So then this icon will be the rotating during the on running. Then after that, this icon will be changed to the number in the bracket. Then it completed. Until this one, so please wait for execution. Then from now on, I'm going to talk about the procedure of the MD simulation. So first step is a setup of the simulation systems. So this step is building the simulation system from the PDB file or other structure file. So this procedure is quite important to run the MD simulation. And following, so outside software will be used So VMD, charm GUI, or Amber, Bromax, charm, also on. And in particular, the second one is the charm GUI. Is that we collaborate with these developers, and this software can generate Genesis input directly. So yeah, we often use this software. And this procedure is not today's focus because this is not our software. However, we also prepare instruction on how to set up the simulation system because this procedure is quite important. So if you are interested in, please find this introduction from this link. So second step is a minimization. After the set up the initial structure, but this structure often contains a non-physical static classes and or unstable geometry. So at first, we need to remove such unstable structures by minimizing the potential energy of the simulation system before the production run. So from this step, we use the Genesis, our software. So this is a whole set of the control input of the Genesis for minimization. So I would like to briefly introduce this input first. So in Genesis, this input is divided into several sections. So each section shows in the such kind of keyword inside the brackets. So input, output, energy, or so on. So first, this is the input. So this means input files for the MD simulations. So input file is somehow the parameters for the energy function or atomic coordinates, so on. This is this section. Output means of course, so input and output. So then output is a result from the MD simulations. So for example, DCD file indicated the name of the trajectory. The trajectory is a set of the atomic coordinates given from the MD simulation. And RST file means a listed file. Using this listed file, we can continue the MD simulations one by one. So, and the third one is energy. Energy section means a force field or a potential function for the Newton equation. So this one. And the blue one is a minimize. Because this is, simulation is a minimization, so then we set it, the section is a minimize. So, and this, please see that n steps, it indicated the number of steps for the minimization. And so and this N out period, CR out period is a period of the period. It means the frequency of the output energy or coordinates, trajectories. So in each. So that is the explanation for the control input. So if we execute the MD simulation, then Genesis output the file, log files. The output, we call it the output file. So if you can get the output file, you can see that 7 paragraphs in the log file, the step from the step 0 to step 6. So each step has information, different informations. For example, so the step 0 is the information for the compile or computation environment. It means the computer system. Step 1 is a parameter that you set. So this means the option or you set in the control file I showed in the previous page. Step 2 is a information of the parallelization. How many processes or threads in the computation node. The step 3 is the information of the molecule and energy function. I think as for the MD simulations, I think this information is quite important. And after that, this 0, 2 to 3 is the initialization, information of the initialization. After that, from the step 4, the actual calculation is 30. First one is a single point energy using the initial coordinates. Then in the step 5, actual minimization cycle. So in this one, so that's showing the energies, properties during the simulation. Then finally, so we Genesis can show that elapsed time that we use. Then I'm going to show the example for the step 5. So during the minimization, so I say so that in the minimization, the potential energy should be decreased. So in this log file, you can see that step 5, and each step you can see that the potential or some of the energy value in the each steps. So this second column is the potential energy, and this is the root mean square gradient. So from the Python script in the GitHub, so you can see that energy changes are like that. So during the simulation, my minimization cycle, the potential energy is going down like that. Then it go to the plateau, or almost constant. Then we can see that minimization is fine, like that. Third step is equilibration. After the minimization, we need to set the temperature and box pressure for the simulation box. So to the target one. So in this tutorial, so we need to run the equilibration using the 3 steps. So first one is a NVT ensemble. NVT means a constant number of the particles and volumes and temperature with a positional restraint on the heavy atoms. So if we set in the temperature, so protein can be the unstable during the setting temperatures, kinetic energies. So then we need to apply the positional restraint to prevent such the moving. So that is the first one. And second one is a NPT ensemble with such kind of restraints. NPT means a number of constant pressure and temperature. And so third one is a similar one, so the same one, similar one. So NPT ensemble, however, so the positional restraint is slightly different. So we have to execute the equilibration using the different conditions or different positional restraints, and go to the system to the relax and set it the temperature and the pressure will be the good. So I'm going to talk about later. So this is a control input for the equilibration using NVT ensemble. So this is a control input is the most part is some part is similar to the minimization. However, this is MD simulation, not minimization. So different section is shown up, dynamics and ensembles. So first one is in input. in input, so that this red one is a reference of the positional restraints. And the second one is the dynamics. Because this is a FD simulation, so then we have to set it the dynamics. So the first one is the integrator. So integrator is somehow the how to solve the Newton dynamics, as Sugita-san showed in the last path. So in this case, so we use the velocity Belle integrator, and this is a time step. So this is a time step for the MD simulation. So unit is a picosecond. And as for the ensemble, I told that this is an NVT ensemble. So then we can set it that this ensemble information here. So ensemble method, MVT, and set it the temperature. So 298 Kelvin. That's right. And as for the positional restraint, we use the selection and restraint section. Then we can set this positional restraints. So this is a control input base. So if we run this input, so we can get the log file from the Genesis. So we need to check the temperature because this should be the NVT simulation. In the step 5, energetics and kinetic properties are shown. So this is one line to the Genesis output in the step 5. So this is the step number, the time, and the total energy, and the potential energy, and the kinetic energy, and each energy terms, and so on. And this one is showing the temperature. So then, at first, this set is unphysical temperature. However, eventually this goes down and set to the constant and the quite similar to the target temperature. So then it might be okay. Then we can change to the next one. So the control input, the incubation using the NPT ensemble. So I extracted the input of the second and the third one because that is almost similar to the first one. The different part is the ensemble section. Because this one is an NPT ensemble, so then this ensemble parameter should be the NPT. And we need to set it a pressure for this one. And as for the third equilibration, we run the less simulation. That is the multi-time step simulation. I will not talk this one so briefly, but we can set this integration so also. Then in order to check the simulation, in the NPT simulation, box size can be changed, can be changed. Then, but however, if the pressure to be the constant, the box size should be the similar, the reach to the constant. Then we need to check the box size is become to the constant. So in the Genesis log file, we can see that here the box XX, box XY, and box XZ terms. This one is x-axis, box length between for the x-axis, y-axis, z-axis. So from that, so then we can see that the x-axis for the box length. So then this one is goes down and become to the constant. This one is the second one. After that, during for the third steps, we can also check the box sizes, and then, so this is a pressure adjustment, time difference of the box sizes. So you can see that the box size becomes almost constant for the each during the MD simulation, then we can see that this almost leads to the target pressure and target temperature also. Then finally, we can carry out the production run after the incubation. In this tutorial, production MDs were executed for the input 1 to input 5 sequentially. However, this files, the condition is almost totally identical. So in actual research, so we need to run the so long simulations. But so because this is a limitation of the time, so then in this case, so it's not so long simulation. However, actual research require much longer calculations. After that, then we can get analysis. We can get the trajectory from the MD simulation of the production run. Then we can analyze the energetics, structure properties from these trajectories or output file. Today, I will show the 3 examples for in the handout. First one is a convert trajectory to place a water molecule inside the simulation box. It means that during the simulation, water box can be the go to the outside of the first set the simulation box. However, during the simulation, we apply the periodic boundary condition. So then energy calculation is fine. However, the trajectory can be it looks the water molecule that goes out. Then we need to convert the trajectory. So then that's the first step. And the second step, the extract protein molecule from the trajectory. So as Sugita-san says, so the water protein is existing in the water molecules. So then we can extract only the protein molecules from the original trajectory. And the third one is we can calculate RMSD. RMSD is the root mean square deviation. So that means how protein change the conformation. So I will show the 3 examples of this handout. Then this is the procedure of the MD simulation. Okay, then now it's finished to explain the procedure. Then shall we go on the actual tutorial? So please see this page 7, and please click this link and go to the Google Chrome page. So if you can see that, you may need to, you can see that this website. I give you the 3 minutes from now. So please access this link. So can you connect this one, this website, Google Collaborate? So if not, please raise a hand or somehow raise a hand. No? Everybody can access this site. You can see that this one. Okay, good. Then shall we start this website? So, okay, great. Then, so this is a tutorial on Google Cloud. So this one, as I told, so that this one is also given from this website. If you are interested in, you can check this one later. So as I told, so today's procedures inside this script, all of the procedure is inside. So first one is a preparation, setup, minimization, incubation, production, and analysis. Then first, shall we go to the preparation? So please download material from GitHub. So I prepared all of the material files on the GitHub. So then please download this material. So in order to that, so please go in this gray shade box and click and enter the shift button. Then this is rotating this icon. It takes time. Oh, then you can see the log of this one. Okay, then if you see the resolved delta sub 100%, it will be okay. Then please do that. Okay, so if you can't do that, so that you can't see that this message, please raise a hand or sign inside this members. Are you okay? Okay. Oh, good. Yes. Yeah, that's good. Yeah, you are great. Okay, so then you can check if you can download the data correctly. So please execute this command like that. So if your download is okay, you can see the two directories like the Genesis tutorial with Python and sample data or so on. Are you okay? So if you have any troubles, please don't hesitate, raise a hand. Okay. Okay, then, so we also use, as I told, so for this tutorial, we use the following Python modules outside. So py3d-mol and matplotlib. I think some of you may know that. So the first one is to see the molecules on the Google Colab. py3d-mol is a quite good tool, I think. So then py3d-mol can be installed on our environment using the pip. So please enter this shade box and enter shift return. Then I think it takes a little time. Okay, but it finished. So please go ahead. Are you okay? So if you have any troubles, please raise the hand. Call me. Good. Yeah. I saw that chat. Really good. Okay. So then as for the matplotlib, so we can just import for this one because this module is already prepared. Just this one and shift return. They don't show any log, but I think if you go to this one, so then you can see that this bracket, so then it's fine. Okay? Okay. So then let's go to the tutorial materials. Then first we need to change the directory for using this one. If you can do that, so you can see that message. Then please execute the ls command. I think you can find the 5 directories for each steps. 5 directories here. This one setup, minimize, equilibrate, 4, 3, and 2 notebooks. I saw the one error. No such directories. So can you say the BN Sarma Thailand-san? So could you turn on his or her microphone, please? So what is the problem?
Yeah, I find this error. I cannot find this directory. I don't know why.
Yeah. Okay. The other students suggest. Yeah. Yeah, that's good. So, is that okay for the Salma-san?
I've been checking.
Yeah, I'm looking for you. Oh, okay. I can find you. Salama-san, are you okay?
This error. I don't know. At this point, I should be writing this.
Yeah. Thank you. So other guy that suggested the Andrea-san. So have you completed this first shell? This one?
Yeah,
Is that
I completed that.
so? Then you can get this message. No. So did you see the did you try this second box?
Yeah, I'm trying to do it again from the start.
Then you can see that this one, no? You see that this directory if you did that.
Can someone share this code in chat?
Ah.
I changed it previously
So
only for this.
So coordinator さん、the administrator, so can you share the hotspot? Is it okay? HP school. So, intern さん can you share the hot screen or no?
Yeah, now I can access that.
Now you can do that.
Yeah.
Okay.
I'm
Good.
sorry.
Good. Then you can see that these directories.
Yeah.
Okay. Good. Great. Then go to the setup. The first section, the setup. Setup is, as I also that this is a quite important procedure. However, it's not today's focus. So yeah, if you would like to interest in, please access this page. So you can see that initial structure using the Py3D. So we install in the Google Chrome. So please go to this setup section directories, and you can see that this one, and inside this one, inside this directory, please execute the second command like that. Then I think you can see that simulation box on the web browser. So this is a white ball is a water molecule. So green one is a chloride ions, and yellow one is a sodium ions, and protein should be the blue one. However, because due to there is so many water, we can't see the protein. If you would like to see the protein, so please click this one, this line, and enter the sharp. Then please execute shift enter again. Then, yeah, water molecule is not water molecule disappears. So then you can see that protein and ions. So can you see the protein and ions? And during in the this script is a really the module is quite great, so that you can change the direction. So if you drag these molecules, click and drag the molecule, so you can see the different view. Or if you rotating the foil, then you can zoom in and zoom out the proteins, molecules. So yeah, please enjoy this simulation box. So can you see that molecules? If you can't, please raise a hand. Okay. Oh, you can't? So yeah, please write down your problem in the chat box. Can you, yeah, some people has a problem with that. So if you have any troubles, please write your trouble in the chat box. Okay. So then let's go to the next session. So that as for the, we may go, shall we go to the next session? So the minimization. So as I told, so the first we need to execute the energy minimization to stabilize the structure. So please go to the second directories like that. Then, and we also execute the ls command. Then you can find the two files, int and log. Are you see? Can you see these files? Then int is the int control files. Then as of course, already I told that this input, so then you can see that using a cat command, so that you can see that this input files like that. So this is the, yeah, inputs. Okay. Then, so then you can run the Python script installed in this GitHub and prepare the extract values from the Genesis log file. So then please execute this script using shift enter. sorry, imported this script like that. Then we can confirm the potential energy is decreasing during the minimization using graph. So then please execute shift plus enter. Then you can see the graph as I showed. So I give you the few minutes, 1 or 2 minutes. Okay. If it works, yeah. If it works, you can see that graph, and you can see that the potential energy is going down, so like that in your browser. So yeah, that is a good question. So as for the in this case, so there's something wrong in your setup system. So then in this case, please see that molecule and the check. Of course, first we need to check the molecule using the viewer like that, as a VMD or Thymol or so on. Yes, in this case, so the many of cases that is a failure of the setup. So we have to check that. Okay, if you have any troubles, please raise a hand or write the problem in the chat box. Okay, then we are going to move on to the third step, equilibration. So as I told, so this is a 3 simulation at the equilibration step. Then please go to the equilibrate directly. Then you can see that the 3 input and 3 output log files. Then as for the first input, you can see that the whole set of this input file, if you execute this one. So that is the same with I show you. Then, because there is a log file already, all log files are prepared, then you can check the temperature. This. So please execute it here, this type, and type the enter, shift return, and shift enter, please. So you may see that this graph. So if you have any troubles, please let me know in chat box or oh. Oh, there is some question about okay. We will make a time to answer the question about the simulation. So, but please go ahead. I'm going to go to the next step. Then NPT ensemble with the potential restraints on the heavy atoms. So if you see the that is almost same. So if you execute this, run this one, so then you can see that input file, and you can see that box size that during the simulation, if you run this enter shift. Oh, yeah, I show that there is so many, professional questions, technical questions. So I hope that I would like to, answer this question later. But hey, then please go to the third step here, and you can see that box size, difference of the box size, the change of the box size. Can you see that? Okay, so then as for the production, so can I move to the next session for the production? So then we can go to the next directory using this one. Then, as I told, so we ran the 5 times. I ran the 5 times the simulation. So then you can see that 5 input and 5 log files. And this PDB file is a last snapshot of the log file. So then if you can see that content of the input. And after the simulation, so as I told, so the water molecule can be spread out the simulation box. So then you may need to wrap you may need to the simulation box. So then then only the showing up. So then please see that, execute that. Oh, you can see. Then this is a fine snapshot of this simulation production run, like that. So because I disabled the showing the water molecule, so then only the protein and the ions are showing up. So if you are showing the water molecule, then you can see that water molecule is spread out from the original simulation box. So yeah, I stopped by this step. So please execute. Then I try to answer the questions from first. So is it possible to brief walk through the setup? So please check. I'm sorry, today we can't do that. So then please check our tutorials. Sorry. So questions, is it Genesis based on the NAMD? No, this is a totally different programs. Syntax looks familiar. I think that is but not based on. I think many of the technical term is, of course, the MD simulation, so technical term should be similar. Of course, the common. So then I think that many of the syntax is quite similar. However, that is not related. Okay. Okay, then finally, are you okay? So if you have any troubles, please let me know. What result will be if, sorry, okay, okay, I will answer that later on. Okay, so then, as I told, so Genesis prepared to analyze the trajectory files. So the convert the trajectory, the place the water inside the simulation box and extract protein and calculate RMSD. So please go to this one, analyze directories, and you may please go to the first directory inside that. This is also showing, you can see that the input file and the log file of this one. So this is a input for the Genesis analysis tool. So, but I'm sorry, I don't have enough time to explain this one. But so we have the tutorial page for the explain this one. So later on, please see that. Then we can see that. So yeah, this is a log of this output, log of this result of this analysis tool. So if you show that water molecules, then not only ions, water molecule can be set inside the simulation box, like that. So second one is this one. Second is extract only the protein. So this is an input, like that. So if you so in this analysis tool, if you set this selection section, then you show that which molecule can be the extract. Then the group 2. So then trajectory out is the group, we can output only the selection 2 in this case. Then just see, you can see that, so only the protein is extracted. This one. And this is a final one. So I'm sorry. I would if you can do that. So later on, I keeping these files for a while, so you can try this website later on. So then going to this one and input file. So this is input files, log files. And so you can see that first 20 lines for you can see that the first 20 lines for the RMS files. So then you can see that RMSD from this trajectories. Then also we can show that the time difference of the RMSD using this matplotlib. Finally, then you can see that the time different changes of the RMS. So that's all of the I prepared. Sorry, I'm learning so the later parts of the tutorial. So yeah, Sugita-san, we have so many questions about
the time is now 3:41. Our time is until 3:50.
3:50, yes.
So we still have some time. So you can answer several questions.
Yes. So then I answer up to I think Apiba D-san's question. What will happen if I already I thought, sorry. So P is interpret graph. I don't know. I'm sorry. So Ami O-san's question, when particular time to execute the equivalent with either NPT or NPT ensemble. What will be selection criteria, or do we always need to go to ensemble together as per example? So in particular, I think many cases, most cases, I think, so that we may need to first we set it to the temperature, then we can set it the pressure. We may need to this procedure. So then, if you would like to execute the NVT ensemble, because that is several technical reasons. So first of during the set, the initial set structures has density of the simulation system is not correct. Because to avoid the state crashes, sometimes the water molecules or other molecules set it slightly apart from each other. Then, then the simulation box that quite a less density. So then we may need to set it the good, the reasonable density. So then we have to learn the NPT, even though if you would like to learn the NVT simulation, finally. But before the NPT simulation, you needed to set it to the temperature as a constant, close to the target temperature. So then we needed to learn the NVT and NPT simulations for the even though either of the NPT or the NPT simulation for the production run. So that is my understanding. So yeah, so the another question, second question, if I'm not wrong, the target temperature, if I'm not wrong, the target temperature, we just confirm that simulation reach out our next simulation.
Yeah, actually, it's related to the.
Okay. Please.
Actually, it's related to the previous question. It's about NVT, the constant you said. You say that you make the temperature constant as value, and then you set pressure as 1. But from the graph, it shows the temperature around 62 and 63 angstrom. So I just confused if the setting.
I see. Okay. Of course, the quite deep. How to say that? So yeah, even though the setting, the temperature or pressure is the target value, but so then at this moment we in the simulation system, so there's a range of the some value of the fluctuation using how to say that. So so then because that is the temperature distribution should be we should have that system has somehow the distribution of the temperature, not constant, exactly constant. I'm sorry. So then you can see that the box size should be fluctuated. However, not the diverse. Of course, temperature is also so that average of the temperature should be that target temperature. So then we open the check this average of that temperature, average of the temperature during the simulation. Okay. So that I'm going to the next question. So what result will be if we skip the minimization step? I think that because if we keeping the such as the strict structures or unstable structures, so then energy should be go to the quite low, high energies. As you may say, the force is a deviation of the energy, then it shows that quite large forces. Then simulation will be crashed. And the water, in the good cases, some molecule goes to the somewhere, or a protein or a cluster breaking, or sometimes the simulation calculation is stopping with the failure. So then I think I recommend that you may need to, try to check the stability of the protein during the equilibrations, by the equilibration state. Okay. Dr. Kobayashi, can you explain relevance of the MD plot of the MD to stability of system, or at least on the conformation structures involved? So I think that RMSD, quite difficult also. RMSD should be the one indication for the see the stability, so the protein does not move to so much. Or so RMSD is this protein, how the protein changes that structure. So then if the RMSD is keeping a constant, but so that this protein itself is not always stable. It's not so simple case. It's not. I'm sorry, quite difficult to answer that. So, Sugita-san, do you have any idea to answer that? You are muted. Sorry.
So you mean the minimization?
No. I see that
Which
can you relevance of the RMSD plot of the MD simulation to stability of the system?
The RMSD is a measure how much the protein structure is deviated from the starting structure. So if it is small, it's close to the starting structure. In this sense, it is good measure for the stability. However, it's just one single value for protein, and we don't know if the RMSD is small, it's okay anyway, so it's stable. But if it's large, so there are many reasons. So for instance, local structure unfolding may happen, or very large domain motion may happen. So we don't know the reason of the large RMSD values. In that case, we have to investigate more. So I mean, computing other structural properties. But anyway, if it is small, anyway, it's stable. That's is promised, I think. Is that okay?
Thank you very much, Dr. Sugita.
You're welcome.
So now I think it takes we need to finish to the our lecture. So because it almost the past 2 hours. So then yeah, that is all. So if I didn't answer the all of questions, so but later on we would like to answer the all of questions. So thank you very much. Thank you for joining this lecture. So I would like to return the time to the administrator san.
Yeah. Thank you so much, Dr. Kobayashi and Dr. Sugita, for the session. Let's give a round of applause before the quiz for our lectures. Yes, thank you. So later on, if you have further question, maybe we can share the presentation materials and also the emails, right? Okay, so the quiz is ready now. Let me check with our technical team there. Okay, we're ready for the quiz? Yes? Okay, so go ahead, it's in the chat. Thank you. It's on the 10 minutes today.
So then